Let's say we were to perform an experiment. So we have a frictionless plane. We have a block on it, and the block is attached to a spring. And then let's say we get our marker out, and we mark a spot on the floor, and we call this spot x equals 0. Okay? And then let's imagine that we displaced it slightly, so that at some later time, we've stretched it out to some further distance. So now we still have our mark for make x equals 0. Now we have a new mark for x equals a, and then we let it go. And we notice, of course, that it's going to oscillate, and then at some point it's going to be compressed, and we'll find it back at the spot x equals minus a. So we do this experiment a large number of times, and maybe we set up a video camera so that we can actually plot this block's motion in every instant in time, or at least in a lot of very small time steps. And so we notice that it's always going to go from x is plus a to x equals minus a, so it's going to go back and forth between these two extremes, but it's not going to do so evenly, right? It's going to be moving faster as it's closer to the equilibrium point and slower on the sides. And so we do this enough times that we see that we can actually write an equation, and that equation is that x as a function of t is equal to a times sine omega t. Okay, and this omega is the angular frequency. So in other words, a block that's moving back and forth faster is going to have a faster angular frequency, whereas something that's moving back and forth much slower would have a lower angular frequency. Okay, but now let's see what this means. Well, we know that velocity is the derivative of x with respect to time. So in this case, that's a omega cosine omega t. And then we know that acceleration is the second derivative of x. So taking another derivative, we get minus a omega sine omega t. But this is just the same, omega squared, because we get another factor of omega. So this is just the same thing as minus omega squared x. Right? So in other words, the acceleration is just minus omega squared x. So we have d squared x dt squared equals minus omega squared x. So this is what we would call a differential equation. It's an equation that has both a term with a derivative, which is in this case is a second derivative, and a linear term. Of course, differential equations can be much more complicated, but we're not really going to go into those in any depth in this class, except to note that we know that the solution to this equation is, of course, x is equal to a sine omega t. But what we also notice is that if we set the force equal to mass times acceleration, which in this case would be minus m omega squared x, and recall that we already said that a spring force is minus kx. So in other words, k is equal to m times omega squared, or the angular frequency is going to be the square root of k over m. So this tells us how we can find the angular frequency of an oscillating block if we know the Springs coefficient and if we know the mass. So the only thing that I'll mention real quick back to this differential equation is that the most general solution, we can have x of t is equal to a sine omega t plus theta, which is also equal to a cosine omega t plus phi. Because sine and cosine are related, they're the same exact function, but offset by a factor of pi over 2. So so any kind of motion that we have that has basically this differential equation is going to have a solution that looks like a harmonic oscillator, which is what this is, these oscillations. And so you can start to see why this is useful. It's because of this differential equation, and because of this solution to the differential equation. We see that A is the amplitude of the oscillations, right? It's the amount that we were originally displaced. And sine and cosine, those are always going to be between 0 and 1. Between 1 and minus 1. So, we go from plus A to minus A, and this omega t, so omega is describing how quickly in time, we're going back and forth.